not going to be robust to outliers, and we'll see that in a little while. What Hartley and others proposed is a distributed approach to solving this particular problem, which arises in the following fashion. So imagine you have the same kind of graph problem. Well, okay, so here's the basic idea. So in distributed computation, essentially what you have is there's a whole set of algorithms called methods, which are based on the notion of consensus. So the idea is that, let's say, forget about the computer vision context here, but let's say you have a same graph and you have a bunch of values at individual vertices, and you want to compute their mean, but there is no central observer. There's no one individual observer looking at all those individual values in the graph. So what you could then have these individual vertices communicate their values to their neighbors, right, one step away. Okay, and so they can exchange that, and then they can do their local averaging based on that. And it can be shown that if you repeat this iteratively, it's going to converge to the mean. Okay, so now this arises a lot in, say, for example, wireless communication kind of scenarios where you have low power, because then you cannot broadcast your signal back to a central observers, right? So individual sensors can communicate with things that are in their local neighborhood, but then eventually they can actually converge to an average answer. And what the so-called Wiesfeld algorithm that was proposed many years ago is a robust version of this. So what it does is, it actually, given these values, essentially it asks the question of how to do this averaging or finding the mean in an L1 sense. So it's a placement problem. So the idea is, if I have a set of points in a plane, let's say, and I want to place a central location somewhere, and I want to minimize the sum of the distances. So this is the so-called warehouse problem, right? Let's say you have many shops and you have a central warehouse. Where should you locate the warehouse? You would want to locate it such that you minimize the sum of the distances to each one of those individual stores that you have, right? So that's an L1 distance, And so there's an iterative algorithm that Wiesfeld had suggested for doing this many years ago. And what it simply does, and what Hartley and others did, is adapt that to solving this distributed averaging on SO3 in the following fashion. So it says, let's say I have a set of values which I have a current estimate of the individual vertices, and I have these relative differences, right? Xij is given. Yeah? So what you would do is, all of these neighbors are going to tell this xj to update itself such that it is more consistent with these differences that it observes, right? And then you do that for the other ones, and so on and so forth, and you keep repeating this till convergence. This is, in a sense, a way of solving, it's one way of solving this problem, but it's doing it robustly, because the measure that or the distance metric it's minimizing is essentially the one, is the L2 one. So it's taking the L2, it's taking the absolute distance and not the sum of the absolute distances, and not the sum of the squares of the absolute distances. And that, as you may be familiar with, is more robust than just taking the least squares approach. Okay, so I will stop here for a little while, and we will convene back. Normally our break is supposed to be for half an hour. I don't know what you guys want to do. We started late, because so if we take half an hour, we're going to take longer. So should we try and come back in 15 minutes? Is that okay? So if I give you a bunch of points on measures, I want to find a midpoint, a mean point, such that it minimizes distance on the scale. So in a vector space, that's flat. So the distance is just 3 degrees. That's the case. But if you're on a sphere, what is it? It's the angle between corresponding vectors. It's the arc length. That's nonlinear. So when you say mean, you're just trying to translate the kind of notion to the continuous. We define a distance metric. So think of mean is there are things which are not consistently together. I want to find an average. What is an average? What that is equal point in some. So I define a distance metric and I say find me a value which is as close to all of this.
Each one of those points
is on the group.
So it's composed of all the rotations and all the patterns.
No. Each point is just one rotation. Point is just one rotation.
But I mean, you're saying
oh, no. Yeah. That's because we are trying to find this. So there are two different things. Maybe I'll just leave it. So the point is, yeah. So this is not a mean. This is just sort of average. It's averaging all of the edges to give you the value given. That's different from individual values. So maybe I should clarify this. So think of this as absolute averaging. Given a set of points, find their mean. Relative averaging. Given differences, find a solution that is consistent with their mean function.
in this case, all each
Right.
rotation is actually R.
Yes.
It's
On
not
the
just
group.
rotation. It's all N. It's not R.
So that depends on what your inputs are. If your inputs are R, you can
Because relative motion is only
yeah, but you can also just do it for rotations. That can be decoupled. That is, you're right. So if I take two rigid R1, and I take the cut, the rotation part is just I can just treat it depending on.
The first is like compare the computation average, like in Venu. How does this actually compare the innovation or converting the innovation axis multiplied by
Yeah. So when you fall apart, yes, and that's not a very good because that is not respect. So people bring stuff.
yeah.
So let's do it. I'll show you some comparison.
Okay.
But also, like, you have trouble doing that with. So if you're not doing these squares, actually, so in that case, so if your noise is small, it doesn't matter. So large, and it's your outliers. Essentially, taking care of what you're saying is ignore the curves. Right? We do it, but this one is not okay. He is not necessarily a technical. This is respecting the other.
And then my second question is, like, if you have some weights in your graph, let's say,
Yeah, you can take care of it.
Oh, yeah.
Well, I think about the results, but I see that there are lots of people who are not familiar with this.
Just yet.
Right. Yeah. So there's a so it's homeomorphism. Yeah.
So are you going to talk about this way, right? This this part. It's kind of give us some commutative extension of the potential vector.
Yeah, in vector space they are commutative, yes. Delta xi's,
Right.
these are commutative. This is commutative.
But I mean, you add in bracket, so if it
This is commutative. In the Lie algebra,
yeah.
the Lie algebra is a vector space.
Yes.
In the Lie algebra, operations are commutative.
But I always no, I don't know. Maybe my impression is wrong. No, I always like that same vector. So you add two vectors together.
Yes.
Like then if like the exponential mapping is kind of different than two opposite vectors. It's
Sure, absolutely. But yeah, I mean, I didn't have the time to develop this whole
yeah.
thing.
I know. But I still think it's kind of this step is because you're adding.
So this is essentially can be shown. I'll refer you to a paper of mine. This is my last year time. It's called Robust Relative Rotation.
Okay.
Yeah, and that actually shows in a different manner that this is nothing but like a quasi-Newton step. I mean, in a different sense, if you want to ignore the group structure, you just look at it.
Okay.
See, the point here, you're absolutely right. If you, so I'm doing, say, mu inverse xi, I'm doing the local, so I'm sort of now centering my origin identity at mu, then I'm writing the tangent space there.
Right. But different factor, they're not in the same direction.
No, of course not.
Right.
But, and those are all delta xi's, the small delta xi's.
Yeah.
And I'm just going to take the average, and then exponentiate it. Right. That. So your question is, how am I allowed to take this sum?
Yes.
That's because there are elements in there. That's because up to a first order up to a first order. So the idea is,
But the assumption there's
no, it's not. See, it's okay. Let me put it this way. What you what you should have, what you're right. What we should have done is write a VCH or VCH or nested VCH form. And you're going to get something. You're going to exponentiate that. I'm going to say, okay, let me put it differently. Forget about this.
Yeah.
Think of gradient descent. Let's say you have a gradient direction, which is expensive to compute. Can I take an approximation to that? No. An approximation of the gradient itself, something like the gradient. As long as it is in the descent direction, yeah, fine. So if you think of Gauss-Newton will just demand that as long as the Hessian allows you to follow the descent, then I can move down, right?
Yeah.
So I'm just going to write an approximation as long as. So the point is, if you have think of a convex cost function.
Right. I agree this will take us down to
Right. So
yeah.
the key point exactly. So the key point is to show that this is a gradient descent step. It is not exact gradient.
Yeah, but hold about this.
So this is yeah. If you go look at my paper, so this is robust. In the sense that this is probably optimal, provided this set is not scattered.
That there are small codes.
Yeah, well, so there's a specific, very specific sense of the sectional culture. So there is this notion of sectional culture that we know in manifolds. So points. Essentially what it is simply saying is think of the circle problem. What do you have? I have 2 points. I move, no problem, I'll keep moving the arc. There'll come a point where suddenly the geodesic switches, flips, right?
Yeah.
I don't want that. As long as I can guarantee that during my entire operation, the geodesics are not going to flip, there's a unique one. Yeah, so inside that. So the idea is you define this ball such that everything is within it. Then you can be sure that you will never do that flipping. The geodesic is going to also do it smoothly. And therefore, you will be.
Okay, so this in the next half of this lecture, we'll talk about some scenario. So I saw this.
Yeah,
I read this.
Yeah, so till
right, that's my question.
So there is a paper in CVPR, I don't know which way it is, which claims it comes from different. Let me just think back to this.
Oh, sure.
Okay, so okay, so let's get back to this. What we did till now is we looked at the group structure and we tried to address the question of how do you do motion averaging on the groups. But there is this other problematic business that we have to deal with real world data, which is the presence of outliers, right? So there are many, many scenarios where you can have outliers in your features representation, which can give rise to gross camera estimation errors. So in other words, what it basically means is that, you know, if I give you these individual motions xij's, some of them can be completely wrong, right? Because they're poorly defined for some reason or the other. And if they're completely wrong, then, you know, if you take the least square average, then you're going to be in trouble, yeah? So let me point out to a few scenarios. So you can have, so you have, for example, this tower, and somebody went and took pictures around it, but the tower is symmetric in nature. So when you do matching of image features, you can actually match features from different facades, right? You know, if you, let's say you do SIFT, you run SIFT on your images, and then you do SIFT feature matching, they're going to look very similar, right? If I have, for example, you can see this, you have this geometrically repeated pattern, and if I take multiple images of this door and then try and find matches, then what will happen is I'll get many wrong matches because they're repeated patterns. Things look locally the same, right? So this is a very big problem, which is illustrated in this case. For example, here you have 2 facades of buildings which are actually, these are unrelated, right? They are not the same part of the building face at all, but they're, you know, it's repeated. Man-made structures tend to be repeated in nature. So you will get lots of matches which are actually grossly incorrect, and they'll give you completely wrong estimates of the underlying relative motions. And you can also have, even if it's the same region that you're looking at, you can have features that are locked on to the wrong repetition. So for example, like I pointed out, you can have a feature at the top left corner on the top left pattern, and it can match any one of those things, you know, with small variations, and then you're going to get completely different, you know, incorrect answers, if you will. And now once you have this underlying problem, you know, there's more of this, right? So if you have an object, you go around, take pictures, they start looking the same, but then you're looking at the completely wrong part of the scene and matching them. So when you put all of these things together, the bottom line is very simple. You cannot resolve this just by looking at pairwise relationships. So you need a global picture to be able to resolve which ones are inconsistent. So you have a set of relationships, those MIJs that I talked about, And now this set of relationships have to be averaged in some sense, but some of them can be completely wrong because of this problem of feature matching or any other source of errors that you may have. This can happen in 3D structures also. So, if you're not careful with doing things robustly, you'll get answers which are wrong. So this is the correct 3D reconstruction of courtyard of a building scene, and because of the poor filtering out of bad matches, you get a reconstruction of this kind. Okay, it's completely wrong. So what you want to do is to have different ways of actually resolving this problem as you solve for elements on the group. So now our problem is getting more difficult, if you will. On the one hand, you have this complexity of the group structure that you need to obey, and on the other hand, you also have outliers in your data that need to be handled in a robust fashion for you to be able to get correct solutions. So you can, and similarly, so for example, this is a 3D reconstruction of a set of scans. If you're not careful, you're going to get garbage like this. Yeah, they don't work at all. Yeah. Right. So, what's happening here? So, for example, let's say you have, excuse me, one edge that is wrong because of the bad feature matches, right? So then it's relatively easy to resolve, because you can then say, if you just do. So let's step back. If you have one edge that is wrong, it's going to contribute a wrong equation to your system of equations. And if you do least square solutions on that, you're going to get garbage, right? I mean, essentially, you're going to get very poor solutions. So what you need to do is to find a robust way of dealing with this. Now, the robustness in the literature, in computer vision, there's a lot of material on how to do robustness. Broadly speaking, you have two ways of doing it. One is you figure out which ones are outliers in your data and get rid of them. Ransack and the whole body of work related to Ransack is on that class. The other is the so-called M estimation from statistical literature, which basically tries to do estimation in the presence of outliers. And we will look at solutions of both types. So, consider a view graph of this kind. And let's say you have one edge which is wrong. It's a poor outlier. So then what's going to happen is, if you were to take this path, it's going to be inconsistent with this, right? Let's say this path is clean. So then it's going to be inconsistent with this outlier. So you can take multiple paths, and then you should be able to figure out that there's something wrong with this particular edge, right? Yeah. So in some sense, the inconsistency with alternate paths in a graph should allow you to figure out which ones are outliers, okay? So because if something is an outlier, then it should not be, if you create a loop here, the overall error should not be 0. It should be high, yeah, because it's not consistent with the rest of the data. So essentially, loops of transformations should yield identity, but they don't in the presence of outliers. And so now you need to have a way of figuring out, using this to figure out how to, which ones are outliers. So right at this point, we're in the realm of trying to identify outliers in a graph. So you're given a set of edges in a graph, and you want to figure out which ones are outliers and which ones are not. You can imagine doing Ransack on this, right? So most of us should be familiar with Ransack. So the idea is you take a minimal solution, and then you check for the number of edges or observations which are consistent with that minimal solution. You do that for a certain number of times, and that allows you to figure out which ones are outliers and remove them, right? That's the standard vanilla version of doing Ransack. Excuse me. Except that in our case, the minimal solution would be a spanning tree. Remember, because we need to have a single connected component that allows us to traverse the graph, right? So the minimal solution would be a spanning tree. And so you can run this. You can sort of run many spanning trees on the data. So if I have a spanning tree, what do I have? Then I have individual edges. I start somewhere. I traverse the tree, and I can read off the individual motion estimates on the vertices, right? So, and then I can use sampling on these spanning trees to actually figure out which ones are inliers and which ones are not. you can do this, but the problem is you have to do this for a very large number of spanning trees to get good bounds on the reliability of your solution, and there are lots of different heuristics you have to use, so it's not all that effective. There are some papers, including this is an old paper, this is from a paper of mine from a long time ago. There are also relatively more recent papers which try and combine, I'm not going to go into the specific details, but essentially start with some greedy approach of trying to find a minimal set of edges which are consistent, which are accurate, and then grow from that. So just to reiterate, remember what we have is a set of observations which are relative measurements on edges. They always have noise because you're getting it from some estimation process that you have, but some of them have noise but also a very large outlier component in them. So some of them are outliers and the rest of them are noisy, and your challenge is to sort of figure out which ones are the outliers to remove them. So for example, in this case, you can, if you take this particular path around this vehicle, then you will get lots of different incorrect edges because of the symmetry of the object, right? So the two sides will start matching each other, and then you will get garbage results. So there are ways you can use ransack-like ideas to filter things out. So you can, similarly, for example, this is from this paper, non-sequential structure of motion. If you have a castle, which is again symmetric, you start having the same kind of problems, right? So you need to have a careful way of removing the outliers from your data set, otherwise you're going to get incorrect camera estimates like this, okay? Another approach, which is in spirit similar, simply says, okay, instead of doing something like ransack, what if I just compute the net residual composition of these transformations? So ideally, it should be the identity element of the group, right? If there's no noise in my individual observations, the net composition should be the identity element of the group. In general, if there is only noise, it's not going to be the identity element, but of a certain small value. But if you have a very large error, then the net composition is going to give you a very large error value. So here's the question, right? So let's say I take this loop. In principle, I do not know which edge or one or more edges are outliers. All I know is if I add them up, I see a very large value. I know that at least one of them is wrong, right? But in principle, I do not know which one. But you can think of a thought experiment where you do this for many different cycles on the graph. And from those measurements, you should be able to figure out, like for example, if there are many cycles or loops in the graph where this, with high error, where this edge repeatedly comes up, then it's very likely that this one's an outlier, right? Yeah, so you can now write that as an inference problem, and you can do meaningful Bayesian statistical inference on it. This is from this paper by Zach and others some years ago. And I'm not going to get into the details of how they set up the problem, but essentially they have some way of relaxing this very complicated inference problem on this cycles on the graph, and actually figure out which ones are inliers and outliers. And so, for example, here in this large city scale reconstruction, they're able to identify that these individual edges that they have which are relating cameras from two different parts of the scene, they are not related at all, but the buildings look similar, right? So you get these erroneous matches, and they're able to infer that those ones are the problems and remove them, okay? Now, so what I've shown you are methods which are like ransack-like or inference methods for detecting outliers in the data, right? And once you detect outliers, you remove them, then you do least squares. That's the basic idea, okay? But more recently, what we did is we took a large number of data sets for 3D reconstruction. We took their solutions from standard existing methods, and then we computed the error on individual edges on the graph. So let's say I give you a solution. So think of your graph. I have those Mij values that you have, but let's say I give you the ground truth Mis. then I know how much error I have on those edges, right? And what I'm showing you here is the distribution of those errors on the log scale. And what this is essentially telling you is that there is no clean separation between inliers and outliers in real world data. And this happens a lot, right? So in general, when you're thinking about outliers, you think of points or observations which have, say, Gaussian noise added to them of some small value, and then you have some values which are very far away from this data set. And so they're outliers, they're relatively easy to remove. But if things are all mixed up and there's a gradual distribution, then it's very difficult to decide what is a good threshold, right? So if I have a clean distinction between inliers and outliers in some representation, I can put a threshold somewhere and separate them out. But I cannot do that for a lot of different problems. And so our argument has been that basically there's no good choice of how to classify, a good classification threshold. So what you should really be doing is actually doing estimation in the presence of outliers. Okay? So the so-called M estimation, which I will show you in a moment. And essentially, these are the bunch of techniques, including ours, which actually does 3D rotation averaging in the presence of outliers without actually classifying them as belonging to the inlier or outlier class. Okay? So very quickly, so this is a paper from 2011, I think. Yeah, so it's journal version is called the conference version is called Disco, and the journal version is Structure from Motion with Markov random fields. So what they do is essentially take this graph representation that I defined and also add some other constraints. So they have things like pose estimates, they have GPS measurements, and so on and so forth. So you can add them as priors into your cost function. Yeah? Excuse me. And then what they do is they basically take the group structure but largely ignore it and write it as a discretization of the group problem. So imagine I have a group, but now what I do is I discretize the groups. I sort of do a quantization on it. So then what I actually have is the quantized centers of the cells. And now solving for the individual rotations or motions is nothing but figuring out which quantization cell you're in. So this is like a coarse estimation of the problem solution, right? And so that becomes a labeling problem. So what they did is they took an estimation problem and converted it into a labeling problem. And once you do that, you can do different Bayesian inference techniques can be applied. And I won't go into all the details of the approximations that they do there, but here are some of the results. You can see that you can do very good quality reconstruction. And the key lesson that I want, now we are beginning to see why we want to do all of this, right? So remember the original proposed method that I said, which was the incremental bundle adjustment approach, which is take a few cameras, solve it, keep adding cameras at a time, and keep growing the solution, right? Now that's a slow process. And what this approach is now doing is taking pairwise measurements of relative motions, averaging them in the sense that we defined, and then solving for the 3D points by doing some kind of triangulation. So you already have a reasonably good, it's not perfect, but you have a reasonably good solution, which is very fast in comparative terms. And so now what you have is the bundle adjustment problem that you have to deal with is almost solved because you're very close to the final answer that you want to be at, right? So the nonlinear optimization that bundle adjustment does is much easier now because the solution that the motion averaging method is giving you is already very close to the final answer. So you can do a few descent steps and converge to the final answer. So you can see, for example, the differences that, in terms of time, essentially the run times are much, much faster compared to the original form. So this is their incremental bundle adjustment solution. So look at this. For example, the central Rome dataset is essentially, it took them 82 hours, and now the total in this particular formulation is 13 hours. Okay, and this is a bit old, so I'm sure you can do better than that now. So you've significantly reduced the overall computational time that is required for solving the problem. Okay. Right, so the method that I showed you just now actually is sort of ignoring the group structure. And what it does is, like I said, it does a quantization of the set of the space of solutions, and then does a labeling problem there, solves a labeling problem. But if you want to keep the group structure in place and solve the problem, this is the approach that was proposed by Hartley and others, based on the so-called Wiesfeld algorithm that I mentioned earlier. And here's essentially what they do. The original cost function, if you just consider only 3D rotations, looks like this. It's a least square solution on the distance between the observations Rij and your estimated values, right? But instead of that, if you minimize the first power of these distances, then that's shown, is generally known to be more robust. Okay? So what they do is they want to solve this particular optimization instead of this. The algorithm that I showed you a little while ago, in a least square sense, would just minimize this. Yeah? Whereas what we are interested in this particular context is minimizing this cost function. And this is the approach that is taken by Hartley and others, and it leads to a distributed rotation averaging problem. Maybe in the interest of time, I'm just going to skip the details, which is essentially what I showed you. What it does is it takes the current value and updates it by comparing it with what the edges and the other neighbors are telling it in a robust fashion, and keeps updating it. So this is a distributed averaging approach. And it is intrinsic. It is still on the manifold, right? It obeys the underlying geometric structure. But what it's effectively done, roughly speaking, is replace taking the arithmetic mean in the Lie group with the so-called geometric mean. Yeah? Sorry, the geometric median, rather. So, you might be familiar with, at least in the scalar case, that the median is more robust than the mean, right? It is more robust to the presence of outliers. And so this is the approach that they take. It solves a well-defined cost function, but it tends to be very slow because of the distributed nature of the approach, because you have to keep updating. Imagine I have a large graph, and I update one vertex here. By the time it takes many steps for that perturbation to be propagated to the other end of the graph, right? So convergence can be very slow. So that's what the Wiesfeld algorithm does. And we found that it can also be, apart from being slow, it can be stuck in poor minima if you do not have a good initialization. So what we propose is to do the following, not in a distributed fashion, but in a batch manner. So we take the same cost function that they have, but now pass it through a loss function. So I hope most of you are familiar with the idea of loss functions. So these are some different, so a loss function essentially takes a value and then maps it, it's a mapping, right? So it takes a scalar value and maps it to another scalar value in a robust fashion. So what is it that we are interested in, in robustness? Let's take a moment to think about it. If you are doing least squares, this loss function rho would just simply be x squared, right? Rho of x would just be x squared. Yeah? So then you get back your least square solution. So what happens in the case of x squared is that if you have a large error, then the penalty is quadratic. So what are you going to do? You're going to try and move the solution closer to that particular point to minimize the penalty. And that's going to corrupt your solution. So in statistical terms, what it basically says is that, oops, where am I? Yeah, sorry. In statistical terms, what it simply says is that you have the wrong kind of influence function on your points, right? So the objective that you have in M estimation with, in a robust sense is the following. When the error is small, you want behavior to be least square like. But when the error is large, if you allow it to be least square, then the penalty is huge. So you want it to sort of taper off, and you want to have some sort of fixed cost, or a reduced cost than least squares, right? So L1, for example, is better than least squares because its influence function is better behaved, and it's also convex, so a lot of people use L1. But there are many other forms that you can use, like Kieman-McClure, for example, is a well-known approach in computer vision. You can take fractional powers of the so-called LP norm, and you can try and solve the problem. So just a reminder, so this is where we are, right? So we defined the notion of how to do averaging on the groups, and we left this aside. And I've shown you a bunch of different ways already on how to solve this system of equations. So the ransack or the Zach's method of inferring on loops essentially takes this system of equations and identifies rows which correspond to individual edges to be outliers, removes them, and then just does the least squares, right? Hartley and others, their approach takes this system of equations and repeatedly applies the Wiesfeld algorithm in an iterative fashion to give you a distributed solution to the problem. And what my students and I have looked at is essentially how to solve this linear system of equation with a robust estimator. And otherwise, all of these algorithms are essentially doing the same thing. But there's a lot that is actually hidden here in the sense that the behavior of the algorithm in terms of convergence rates can be enormously different, depending on which particular approach you take. You can take, so it's very, very important to pay attention to how you solve this particular step. Okay, that's sort of the key difference, if you will. Okay, so I've already talked about this. So essentially, you want to have a penalty function which behaves, for small deviations, behaves in a least squares kind of fashion, but when it tapers off in a graceful fashion as you move further down, away from the origin 0. And one good way of, so we want to solve this cost function. So let me go back. We want to minimize this cost function. The question is, how are we going to do it, right? So our proposal is to use the iterative reweighted least squares approach. I'm sure most of you are familiar with it, but if you're not, very briefly, here's how it goes. Let's say I have an AX is equal to B form. I can define the residual error, and essentially in least squares, what I'm trying to do is minimize this term, right? This is just nothing but the norm squared, right? The least square solution. But now I want to take something like minimize a cost function, say, of this kind, where this is, now going to have robustness built into it, depending on the scale sigma that I pick, right? And so what you do in iterative reweighted least squares is to just essentially do exactly what the title says. So you get a solution, you look at the residual errors. If the residual error is large, in the next iteration, give that particular equation lower weightage in a system in a certain manner. And you keep doing this, and you can show that under certain conditions, this is going to converge to a reasonably good answer. Okay? So it's going to trade off robustness versus accuracy. And you need that because almost invariably, I can guarantee you that you take any set of real world pictures, you're going to have outliers in that data. And so you have to be able to deal with this. Okay? So essentially what we do, I'm going to summarize the work in our paper that was in PAMI 2017. If you're interested in the details, you can look it up. So essentially, we want to minimize a cost function of this kind. In the Lie algebra, it begins to look somewhat like this. At any given step of the iteration, you're looking at the residual fitting error in the Lie algebra. And it leads to an iterative reweighted nonlinear least squares problem. Okay? And so it can look rather complicated. I won't bore you with the steps at this point, but it has a behavior of a Gauss-Newton-like form. Okay? So essentially we are doing, quasi-Newton kind of steps in on the Lie algebra. Now, it so turns out that the exact form, if we were to solve the IRLS on robust cost functions, the Gauss-Newton's form, that problem that we need to solve looks like this. Okay, so where Aij comes from the incidence matrix form that we mentioned earlier. It just comes from that plus minus 1 terms corresponding to individual edges. Yeah, whereas B's and C's have more complicated relationships with the current estimate, the current location of your solution. So what we do is we actually simplify the problem, because this is expensive to compute. We just simplify it to solving this. That is, we drop these two terms. These two terms are data dependent, whereas this is data independent. Aij is data independent, Bij and Cij are data dependent, or rather dependent on the current estimate. Okay, so what it allows us to do by dropping that, and we still ensure that in our quasi-Newton form, that the approximated Hessian that corresponds to this representation is still positive semi-definite. So it's going to guarantee that you're going to still move in the gradient descent direction. Okay, so once you do that, you can actually do very fast estimation, because remember I mentioned earlier, multiplying with Aij's is not floating point multiplications, but it's actually just additions, because Aij's is just plus minus ones, right? So if you do the bookkeeping carefully, you can get very fast optimization here. Okay, so I'm going to skip many of the other things that are involved here. We tested a whole bunch of different loss functions. Now obviously the behavior of individual loss functions is going to depend on the exact nature of the outliers in your data, right? And empirically, for a large number of data sets, we found that the loss function of L half does the best. Okay, so it's a very, very busy slide here. I'm not going to bore you with all the details. I just want you to recognize the scales of the problems that we're looking at here. For example, the so-called San Francisco dataset has about 8,000 cameras, so that's the size of the graph, right? You have what, 8,000 camera vertices and about 100,000 edges. Some of them have even more, like this has like, like 600, almost 700,000 edges, right? So we are talking about doing rotation averaging with graphs of, the size n is thousands, and the number of edges are hundreds of thousands, right? And many of them are outliers, right? And you need to be able to do this efficiently. Anyway, so the bottom line, I'll skip the details. I'll just show you one example from the San Francisco dataset. This shows, with respect to the bundle adjustment answer as a ground truth, this is the relative distribution of errors. So if you look at this, so we took all the fitting errors on individual edges compared to our solution, and we just built the histograms. As you can see, if your histogram is closer to the origin, it moves to the left, then you're doing better, right? Yeah. So these are like ROC-like curves, and this blue curve is ours. This is the Wiesfeld algorithm, and it does pretty poorly on this case, and this is the DISCO method, which does the graph inference problem. Okay, now you'll notice, so I also plotted this just to emphasize a point. It so turns out that the Wiesfeld algorithm's cost function that it's optimizing is exactly the same as ours with with L1 as the norm. Yeah, it's identical. The difference is in the choice of the algorithm you use for doing the optimization. And as you can see, this is on a logarithm time scale. And as you can see, our convergence here is very fast. And this goes on forever. And then eventually it drops at some point. But it's essentially doing the same thing. But because it's doing this in this very complicated distributed consensus approach, it's very slow, and it's really not effective for real world applications of this kind. Okay, so I have shown you structures to do with, and I've shown you how to do rotation averaging on the group structure, that is respecting the group structure. But obviously, That is not the only way people solve this problem. And so I'm going to very quickly and very briefly go over other approaches which actually sort of don't worry too much about the group structure SO3, but try and attack or address this problem in a different fashion. So these are essentially what you might call extrinsic methods, because they do not necessarily obey the underlying group structure of the problem, but try and still get to an answer. Somebody was asking me what happens if we just sort of ignore the underlying group structure, take averages, and solve the problem. So here are some techniques which do various versions of that. There's one method that, so you can take quaternions. So in fact, I'm sorry, I'm going to skip defining the forms of the quaternions, which some of you may be familiar with. But essentially, a quaternion is a 4-dimensional unit vector representation of 3D rotations. This is one other form of representing the same rotation form that we are familiar with as 3x3 matrices. And you can actually take the rotation averaging form and write it as a linear system of equations with the quaternion form. So you have some matrix capital Qij, which looks like this, which is from the observations that you have. And Qi's and Qj's are the quaternion solutions of individual cameras that you want to solve for. Okay? So you can solve this as a linear system of equations, except that there's a bit of a, so you can embed this and solve it as a linear system of equations. This is what I did in my first paper on this a long time ago. Except that there's a problem, which is that the stacking of all the quaternions into a single vector and solving it extrinsically ignores the norm constraints on the quaternions. Quaternions are supposed to have unit norm in length, right? So you're going to get an extrinsic solution. So it's efficient, but it's not very accurate because it ignores the underlying structure of the problem. Then people said, well, we can take this and subject it to Lagrangian, and then do a constrained optimization. So the unconstrained optimization would just be a least square solution. Now you write a constrained optimization, so you have a quadratic cost function with constraints of this form. You can write the Lagrangian form, do the primal dual trick, and then essentially you get a semi-definite program to solve. Okay? And so then there are various ways you can solve it. You can incorporate robustness and so on and so forth. So I think one paper got dropped out here. So this is from Fredrickson and Olsen in 2012. It does reasonably well, but semi-definite programs are in general not necessarily very fast, and they don't scale up very well, right? So if you have large data sets, then you're going to have trouble optimizing. Okay, so there's another large class of approaches for doing rotation averaging, which is of this form, which takes, notice this is what we were trying to solve, where this was on the intrinsic manifold, and you just relax it to look like this. So what are we doing here? We're just treating Ri's as 3x3 matrices and ignoring the underlying geometric structure completely. Okay, so you can relax this to this form and essentially do extrinsic estimation, right? And once you do that, then you can actually project it back. I skipped that slide in the interest of time, but there is an easy way of taking any extrinsic solution and projecting it onto the group. If you want to go back later and look at the slides, this is what you should look at. The optimal way of projecting a point. Given any matrix X, you can find the closest 3x3 rotation. This is a classic solution provided by Umeyama many years ago. It's very nice. It just does an SVD. Yeah. So back to our problem. So what do? You take the intrinsic optimization cost function, relax it. So this is, let's say, the Frobenius norm of matrices, right? So now it's just trying to solve for matrices which do not obey the underlying group structure. And now the question is, how do you solve this problem, right? You have this cost function, but you need a way of solving this, right? And so in the literature, the variety of approaches for solving this relaxation which can be called, which can be classified as these three types. There's a spectral relaxation, there is a semi-definite, and then there's the rank relaxation. And I'm just going to very quickly sort of just give you just a hint of what they look like. Okay, so notice what we are interested in. We want to find RIs which satisfy this form, right? Rij, Rj, Ri inverse. So if I were to take all of those such elements, I can write a matrix of this form, right? This is, imagine this is like the full graph, if you will. Yeah? And some of you would be familiar with, this is called the Gramian matrix, right? Yeah. So the reason you can do this is because the inverse of Ri is Ri transpose. And therefore, if I take R, I can write this as, I can write Rj Ri inverse as Rj Ri transpose. And effectively, if I stack all the rotations into a single matrix, vector form of this kind, then I can write the observation matrix G that I have, which is for the full graph, as R as the outer product of these forms. Yeah? I hope everyone can see that, right? Because G of ij, think of the ijth block, 3 by 3 block, is nothing but, you can read off, right? It's going to have one dot product with Rj and Ri inverse, or the other way around. Yeah, it doesn't matter. As long as you do it consistently. So G is essentially the set of all the individual relative rotations that we are talking about. But obviously we should be able to immediately see from this form that this matrix, big matrix, the stacked matrix R is of size 3n cross 3, right? Yeah, this has only 3 columns. Therefore, the rank of G is 3. Yeah, and because of its particular form here, it is symmetric and positive semi-definite. So now you can use this for doing various optimizations. You can use these properties for doing various optimizations. So the spectral relaxation simply takes, it tries to construct G, does, and then just does a spectral decomposition, takes the first 3 leading eigenvectors and pulls out individual blocks and projects them onto rotation matrices. I hope it's not too difficult to see how that would work, right? Because remember, these are all individually noisy, right? These have noise in them. Yeah, so what you're going to do is you're going to take the top 3 eigenvectors. That's going to give you your estimate of this R here. And you pull out each individual Ri, which is going to be a 3 by 3 block. But that's not going to be orthonormal, because you have not enforced the orthonormality constraint here. So you just project it to the closest orthonormal matrix and you're done. And that's the spectral relaxation. Then there is the semi-definite relaxation, which simply says, if I take the estimate of R, I can write it in this, I can write a matrix X, which should be of this form, and it should be positive semi-definite by construction. And so therefore, I'm going to say my objective function that I want to solve is minimize the trace of this form with positive semi-definite constraints on X, and the constraint at xii on the diagonal is identity. It's simply just packaging the original form that we did for spectral relaxation in a slightly different form, right? It's imposing the semi-definite structure on it. So, people have shown that this gives you a better solution compared to the spectral relaxation technique, because you are doing a better job of enforcing the individual constraints on the underlying representation. There is a rank relaxation form. I won't go into the details. It's somewhat complicated, but essentially what it does is it takes, remember, you do not have the full observation Gramian matrix, right? You do not have every possible edge in your graph. You only have some of them. So it takes that particular structure and tries to write it as a low rank form, which is this 3-dimensional Gramian form, plus noise, plus outliers. I mean, you would have seen a lot of these convex optimization methods which came up with, when people were doing sparse compressive sensing kind of problems, right? So you write an observation as a lower rank structure that you have, plus some noise term, plus a sparse set of outlier terms, right? So if you have k-sparse terms of that kind, then you can do different kinds of optimizations to solve this problem. And so this is what this particular method does. In summary, the basic difference is that extrinsic methods are relatively easier to analyze. You'll find a lot of papers which would argue that they have, they will try and show that the gap, they would try and show strong duality, that the gap between the primal and dual is 0 for certain conditions, and therefore their solution is optimal. But remember, that is for the relaxed problem. That is, you do not enforce the constraints on the group structure that individual observations need to satisfy. While that has some interest for sure, they tend to be somewhat slow because any of these semi-definite kind of problems lead to complicated optimizations that are expensive to solve. On the other hand, intrinsic methods are local, can be very fast, and I've shown you that how you can do very fast optimization. You can get very good results. State of the art, it's efficient, scalable, robust, and so on and so forth. But the difficulty is really that we only understand the behavior of these algorithms in a local sense, because you have this complicated Lie group structure and you're trying to prove properties of convergence. All we can prove at this point is that methods are locally convergent. But I've given you a test of one paper which tries to and understand when is that local solution going to be globally optimal. Yeah, but so that's the essential difference, right? So, but I would still argue at this point, the intrinsic method that I presented to you using IRLS outperforms pretty much anything out there. And so for very large scale problems, this is really how we want to do it. Okay, so now I've spent a lot of time looking at rotation averaging because we use the group structure and then we understood how to do this, and now we can actually sort of chug along and do a variety of other things with it. So let's go back to our original projection equation, right? So to start with, so this is the left-hand side, this is the image projection, this is the camera that is not known, this is the 3D structure that is not known, right? Now, imagine I do rotation averaging. So I know the individual cameras R's, right? So once I know the individual cameras R's, I can rewrite it in this form. Well, there has to be a homogenization here, there should be a 1 here, and a suitable modification. But you get the idea that once I solve for R, the unknowns in this projection are now the 3D structure and the camera translation, right? And so that becomes essentially, it's much closer to a linear problem. I mean, except for the scaling of projective relationships, this is a linear system equations that you can solve. So this is now beginning. There are papers coming out in the literature which call it the non-rotation problem, right? So if you know the rotation, then how do you solve for the rest of the terms that you're interested in, which includes both 3D translation and also the 3D structure. You can also, if you remember, I mentioned in the beginning that the original motivation is to completely factorize structure out of the problem. So you can also work with a purely translation averaging problem, okay? And so the problem that I'm going to talk about, I'm going to skip the non-rotation averaging problem and go straight to the translation averaging problem. So let me reiterate. We started with the observation that it is computationally cheap and easy to solve for the relative motion between pairs of cameras, let's say with epipolar geometry, right? But the trouble there was that epipolar geometry allows you to recover, let's say you take the essential matrix, you can recover the true rotation, but you do not know translation up to scale. So for those of you who are not familiar with it, think of the following problem. Imagine I have 2 cameras and I take a picture of the world and I make some measurements. Now, there is a scale ambiguity involved because I could have moved the cameras, let's say, closer and scaled the object appropriately. And I will not be able to, I should not be able to tell the difference, right? So inherently, whenever you're looking at two pinhole cameras, you can only recover the direction of the translation between them, but you cannot recover the absolute scale of the translation between them. So what you have is you don't recover Tij, but a small Tij, which is essentially the direction vector and the direction version of capital Tij, right? The scale is removed. So this is only known up to scale. So it's unit norm. Okay. So it looks simple, and you can actually do some things with it, but it actually makes it leads to some interesting challenges in the optimization, in the context of optimization. So just to differentiate, for the rotations or for Euclidean groups, our problem was really trying to understand the group structure and its properties, and when you can do operations in a careful fashion to do the optimization. Here, you have a scaled observation which leads to other kinds of implications for how you do the computations. Okay, so this got nothing to do with the group structure, but nevertheless it leaves you with certain kinds of challenges that need to be addressed. Okay, so here's a simple solution that I proposed a long time ago, as you can see. So here's the basic idea. You have Tij, which is your observation. Rij is known. The capital T's are not known, and this is a projective relationship. That is, I know this is equal to, the left hand is equal to right hand side up to an unknown scale factor. Well, the naive way of thinking about it would be just take their cross product. They're three-dimensional, take their cross product, you get is equal to 0, right? I have A is equal to lambda B in 3 dimensions. I can write A cross B is equal to 0. Yeah? So then I can set up a linear system of equations and solve for the entire translations in one go. I can do other tricks like reweighting it and so on and so forth. I won't go into those details. They're fairly easy to figure out once you look at the paper. This does okay, but it has certain problems. The main problem is the cross product is not a very informative way of looking at something, right? So if you take the cross product of two terms, you're not going to be able to measure anything about the second term in the direction along the first one, right? I mean, A cross A is 0. So the error along the direction of one of the observations is not going to be penalized. That's one way of thinking about it. So essentially what it will do is it's not going to do a good optimization. It's not going to pose the optimization in the right sense that you want. Secondly, there are degeneracies if you have linear camera motions. So if a camera moves linearly, then all the heading directions are essentially the same, but their scale factors are different, and the cross product is not going to be able to recover that very well. Okay, so that's not a very good way of doing it. So it turns out then people said, how are we going to address this particular problem? I hope you can see that what you have in the bottom are essentially the blue dots are the cameras, right? So if you have edges going the cameras, between cameras, and this is what we have been looking at till now, right? We've been looking at a view graph, where you have a graph of cameras and you have edges relating them. But now what you could also do is add a few of the structure points. Remember, this is almost like your overall global structure from motion problem. In the structure from motion problem, you took everything together. You took the 3D points, the unknown 3D points, the unknown cameras, set up the relationships, and solved them, let's say using bundle adjustment. In the motion averaging setup that I've shown you till now, we eliminated structure, just took the relative motion relationships on the camera-camera graph or the view graph and solved it. But then we now find that when you want to recover translation, that's not adequate because you have degeneracies to do with linear motions, which are very common. So what people suggested is that you could take a few of the unknown 3D points into the problem. Not all of them, but you can take a few of them. and add them to your soup, if you will, right? So now you have a problem where you have camera relationships which are coming from epipolar geometry, but you also have camera point relationships that you can write. And if you think about it for a moment, there is in a projective sense, there is nothing to distinguish camera centers and 3D points from each other. Okay, so they are all essentially you can embed them into a uniform way of looking at them. So there's nothing to distinguish structure points and camera centers as points in 3D space. So once you do that, you can write, you have to massage the constraints in the appropriate fashion, and once you do that, you can address this problem of dealing with degeneracies. So you can sort of stabilize the solution by adding some points. The question is, how do you pick those points? There are all kinds of empirical details that are important. Excuse me. I'm going to skip those particular details in the interest of time and just point to this solution that Kyle Wilson and others did a few years ago called Robust Global Translation with 1D SFM. They use some simple trick to figure out which ones are also outliers. Remember, you want to still solve this problem in the presence of outliers in the data. Yeah? So you cannot ignore that. You can't just go back to your linear system equations and translation and just solve it. Okay? And once you do that, you can set up a cost function which looks like this. So Tij is the heading direction that you are observing from epipolar relationships. And if capital T's are your solution, this is what the heading direction should be. Right? And so you can take their difference and minimize some least squares cost. So this is a highly nonlinear cost function, but works reasonably well. It has certain nice properties, and it can be solved reasonably efficiently with, in this case they used the Ceres package. And here are some of the reconstructions that you can get. So these are fairly large-scale reconstructions, excuse me, which are now faster than just doing incremental bundle adjustment, right? So let me take a step back. So what are we talking about here in the context of translation? We have a slightly peculiar kind of problem. You're not, in the case of rotations, your left-hand side and the right-hand side were both elements of the same group. In this case, what you have is the observations, small Tijs are directions, and your estimators are points are vectors in R3 which actually have actual length associated with them. So you have this sort of incompatibility in terms of incommensurability, if you will, right, in terms of what you're comparing and measuring. So you have directions on the one hand, that's what you're given, and you want to compare them with actual physical lengths. So you would think that the simplest way to do would be to just take the direction component of the length of the vector and compare them, right? And that's what some of these methods do. But the question is, when is it in theory supposed to work? This is an important question to ask. If you remember, we said that in the original view graph, if you do not have enough relative motion such that you have at least a single spanning tree in your data, you're not going to be able to recover a global solution because they are not connected to each other, right? So the question in this case, given the fact that you're getting heading directions and you want to solve for absolute translations, the question to ask is, when do you get a unique solution for translation averaging? That is, what is the set of relative direction edges that you need on your graph, right? What should your graph look like? Now your graph is, you're getting heading directions. What should that graph look like for you to be able to recover a valid solution, right? Cut a long story short, there's a complicated theory. This has been well studied in graph theory, and this was pointed out by Oisiesil and others in 2015, and that it comes from this notion of parallel rigidity. So schematically, here is the basic idea. These are all the observed relative heading directions. And so, for example, this is a valid solution for this. So that is, each one of these vectors is consistent with these directions. Yeah? And so what they're trying to ask is, given a set of heading directions, what is the theoretical requirement that I have to be able to actually get a valid solution? Yeah, this has got nothing to do with outliers or noise. It's just got to do with the minimal set of constraints that you need to be able to solve the problem. And I won't state, it's there on the slides. You can look at it later if you wish. It's a complicated definition of what the properties the graph needs to satisfy, and it's known as parallel rigidity in the literature. Here's what it looks like. I'm not going to go into it, except that there are efficient algorithms for both verifying whether a given graph is parallelly rigid or extracting the largest parallel rigid subgraph given a graph. Okay, so you can start doing these things. Okay, so here is their solution to this problem of doing translation estimation. So here's what they do. They construct this matrix Qij. What does this look like? This is essentially just nothing but the projection in the orthogonal direction, isn't it? Yeah. Yeah? So this is the projection matrix for the given heading direction, and it has certain specific properties. So what they're doing is they're taking the difference in the translations and projecting it in the direction orthogonal to the observed translation component, and they're saying that cost has to be minimized. This has to be minimized. Okay? And remember, again, as I said, there is a translational shift. There's a gauge freedom that you can add, right? For every TI solution, I can add a constant and I can still get a consistent solution. So they impose a constraint that the sum of TI is 0. That's just simply fixing the gauge freedom. And then they impose a norm constraint, because otherwise I can trivially send all TIs to 0. Yeah? And in fact, they find that even solving this, so this gives you a convex optimization problem, but they find that it tends to collapse, in the sense that if things are strongly connected to each other, there's a dense subgraph, all those cameras tend to move closer to each other. So it's not a very well-posed cost function. Yeah? So, so then they did other tricks. They said, okay, instead of having a scale constraint of this kind, I'm going to impose a minimal size, right? So this is what they call a repulsion constraint. So now instead of demanding that I fix the overall scale of the translation problem, what I'm going to demand is that each relative displacement has to have a minimal distance between them. Okay, so it's not going to allow things to move too close to each other. It won't allow the solution to collapse, right? But solving this is now computationally much harder. Okay, so there are various things that they do, with augmented Lagrangians and so on and so forth. You can look this up in CVPR 2015. But they have very nice results. So here are some reconstructions that they have. But notice that there's no bundle adjustment involved in this at all. So it takes the rotation averaging problem, solves it, takes the translation averaging problem, solves it, does triangulation, and you're done. Okay? So obviously this is not the optimal solution you can get, but it looks pretty good. It's fairly accurate. It shows that you can actually get a lot of mileage by just looking at this relative motion averaging idea. Okay? Now, in more recent work, there has been this idea of shape fit and shape kick, I think ECCV 2016. And so what they did was, see, everyone's playing around with the same set of constraints, right? So what they did is they said, fine, we will minimize this orthogonal projection component, but the constraint we will impose is of this form. Notice the difference in how they impose the scale constraint here. Yeah, so they take the absolute difference of translations and take its dot product with the heading directions that you observe, and then they demand that all of this is scaled to some constant. Okay? Now you would think that, why should it make a very big difference? And so they've shown that their method was faster than the previous one that I mentioned. And so here is a quick comparison of what's going on here, right? So there's like, too many different things going on, and I'm not going into the specific details, but here's a comparison. What Kyle Wilson and others do is they take the heading direction and compare it directly with an estimated heading direction in a least square sense. So this gives you a highly non-linear optimization problem that you need to solve. What this group does is, instead of doing that, so this is a slightly different version than the collapsing problem that I showed you. Here what they do is they take the difference in translations, and instead of comparing it with the heading direction, they compare it directly with the estimated displacement. So there's a lambda ij, so they're actually explicitly estimating the scale factors also. And then they have this repulsion constraint. So here you're comparing heading directions, here you're comparing displacement distances, the actual physical vectorial displacements. And what shape fit does is it minimizes the orthogonal projection while imposing a scale factor in a slightly different manner. Okay, so now you have to wonder, like, okay, so what's going on here? I mean, they all look kind of similar, they're intuitively all they are doing is they're saying, look, I have a heading direction, I have a displacement vector, I need to find some way of comparing them, right? And that's going to give me my cost function, right? But in terms of performance, you start to get different behavior depending on how you set up the optimization. So there are a whole bunch of issues in translation averaging, and some of them are very nicely summarized in this paper that's going to come up, I guess, soon. I don't know which day of the conference in CVPR 2018. In essence, the geometry of heading directions is very simple, but because of this lack of the scale that you're unable to observe, you have all kinds of issues and headaches that you have to deal with. So the question is, what should you compare? Should it be direction or distance? We also know that epipolar geometry, heading directions can be extremely biased. If you're familiar with the bar relief ambiguity kind of problem, you have those kinds of questions coming up. You may need stabilization for, if you have linear motions using camera point relationships. And overall, there is still the whole issue of how do you solve this robustly and efficiently. So many of the methods which actually try and, many of them try and say, well, we have this complicated problem, so we'll just set up the convex version, which is essentially an L1-like cost function, because then, I have convex costs with maybe convex constraints, and I can try and work with it. But then that still leaves you with the question of efficiency, because they tend to be slow for large-scale problems. And there's also a question of robustness, because, if you want to be truly robust, you would like to have a very general, you would like your solution to be able to handle a very general class of loss functions. And so in that sense, it's still open at this point as to how to do this. And I think it needs a little bit more careful analysis than we have at this point. Okay, so what have we done till now? We have figured out how to take pairwise cameras, find relative motions, solve for the rotation averaging problem, solve for the translation averaging problem. Well, you solve for the cameras, right? You know where the cameras are. And now you can solve individual, you can use it in different ways. So then the obvious question to ask is this, I started out by contrasting the motivation for doing motion averaging from bundle adjustment, right? So if you look at this schematic idea, it says bundle adjustment is very accurate, but it's slow. On the other hand, motion averaging is very fast, but it's not all that accurate, because the reason it's not all that accurate is because the relative motion estimates that you're getting, which are the inputs for your motion averaging method, are obviously not that accurate. They're just using 2 cameras at a time, or maybe a few at a time. So they are going to be less accurate. So if your input for the averaging is poor in quality or is noisy, then the output is also going to be less accurate. So what you're gaining here is in time. So the obvious question to ask is, can we do some way of sort of integrating these two things? And essentially this leads to an approach that we did a few years ago, and now there are more papers coming out on this on this idea, which is to interleave motion averaging and bundle adjustment solutions. And so I skipped these details, but essentially, if you go back to the paper that Wilson and others said, where they analyzed the difficulty of the rotation averaging problem, they pointed out that if things are strongly connected, then the problem is easy. That's I mean, it jives with your intuition, right? If there are lots of relationships that you have, then the overall problem is easy to solve. So what it suggests is the following, that essentially if you take a very large graph, there are going to be subsets which are strongly connected, right? So if you take a very large region, you take lots of pictures of this room, you go somewhere else, takes lots of pictures of them, and then somehow connect them in between. Well, these two components individually are very strongly connected. They can be solved better. I mean, they can be solved individually very well. So what we suggest is what we understand from that is simply saying, if you have a higher connectivity within a subset, then you have a smaller bundle adjustment problem that's easier to solve. Okay, and that's the basic idea. So it's sort of, I'm going to just quickly schematize it in the following fashion. So let's say this is your view graph. You use some way of partitioning it into individual subgraphs, right? And so now look at this schematic. These are individual problems. So I take the full set of cameras and I partition it. Let's say I partition it into 4 sets. And now within each set, I solve it. I don't care how I do it. I have some way of doing it. Let's say I do bundle adjustment for all I care. I solved it. So now what do I have? I have 4 individual pieces of the overall solution solved, right? I know individually what they look like. The remaining part of the problem now is aligning these chaps with respect to each other, because they've all been solved in their individual frames of reference, right? Is that clear? So what this now translates to is essentially a smaller motion averaging problem now, because you can solve these individual problems, and now there are edges that are going to go from one subset to the other. Those edges give you relative motion relationships. So you can think of this as, I solve this problem of individual cameras within, let's say, this blue set, and I freeze them. That's fixed. I solve this red set, I freeze them, they are fixed. Now, as far as I'm concerned, they are now individual cameras. They're just 2 cameras, right? And so now I have a bunch of relationships which can be written as a single constraint. So what I've done is I've taken this large view graph and collapsed it into a smaller view graph, right? So now you can do a hierarchical way of solving this, and then you can actually sort of aggregate, the relationships across the edges and so on and so forth, and you can do, we call it divide and conquer. And you can do very efficient, accurate estimation. So you can actually speed up the overall optimization much more. You can speed it up. Okay, so the obvious extension of this idea, which is what we did, this came out last year, is an agglomerative method. So you think of the view graph at your base plane, where there are individual cameras, and then you build it up bottom up. So you take clusters, you solve them, and then you move up the tree. Think of it as a hierarchical tree, right? So you take 2 leaf vertices, which are sub-problems, solve them, and then align them. And then if you feel like, you can do a refinement, right? And then you can just sort of move up the tree and you can be done. And there's a very big bonus, those of you who actually work with these data sets will recognize this, is that now if you do this kind of a hierarchical manner of partitioning the original data, then what I have not mentioned till now is that the biggest cost in doing any 3D reconstruction is not in the geometry, it's actually in the feature matching. Right? You spend most of your computational time figuring out which SIFT features match which ones, right? So now when you do this partitioning into a hierarchical form, you're only going to do local sort of nearest neighbor searches for feature matches within each individual cluster. That's going to be much faster. So what, I don't have the numbers here, or maybe I do. So for example here, this is a comparison of our result with that of VSFM. It's very close, right? I mean, there's no real true ground truth for these data sets. Yeah, so it's like, your mean rotation error is never more than 1 degree away in doing this. But the key point here is this is at least 10 times faster than doing incremental bundle adjustment. So you get an order of magnitude speed up. Okay? So here are some other reconstructions. You can look them up later. So in the remainder of the time, so that's all I have to say as far as recovering 3D geometry from regular cameras is concerned. So let me recap. The basic problem we had with the pinhole model was the fact that there's tremendous loss of information, right? You've gone from a 3D representation to a 2D projection, and much of what we did in geometry in computer vision for a while now is figuring out ways of how to undo it, right? And this is one approach of how to do this at a larger scale. But there's obviously the other context where you actually have 3D scans available, right? If you think about depth cameras, if you think about LiDAR and so on and so forth, they are not giving you images, they're actually giving you direct depth representations that you can work with. So obviously there, you should be able to apply the same principles of doing motion averaging, except that now we're no longer working with the rotation group R, you're working directly on the Euclidean group SE3. Okay? And so I'll very quickly, I'm not going to spend a whole lot of time doing this, I'll very quickly go over some ways of using the same principle of doing motion averaging that we applied to the case of 3D rotations to that of general Euclidean motions. And you will see that there's also payoff to be had there. Okay, so this slide just simply shows that, I think there was a question in the break about what happens when you just take individual rotation components. You can see that basically if you take products of two Euclidean motions, the rotation form still retains its own group structure. That's what sort of allows us to de-link 3D rotation from translation. And remember, that's why we do rotations first and then translations later in the case of regular camera images. And many of the things that we mentioned now earlier still apply. The motion groups are now in SE3. They are 4x4 forms here, right? They form the special Euclidean group, and they have 6 degrees of freedom, 3 for rotation, 3 for translation, and they're not abelian, right? So they don't commute, just like you have the same form. The formulae for the mappings are a little bit more complicated than your Rodriguez form, but there are close. Essentially, the bottom line is there are closed form expressions available for moving from the Lie group to the algebra and vice versa in the case of SE3. Okay, here is one big issue. Unlike the rotation group, the distance you cannot have a bi-invariant distance metric on SE3. You can either pick a left invariant or right invariant form. I'm not going to go into those details too much, but this is a huge issue. If you look at any geometric textbook in robotics, you will find this discussed at length because it matters a lot for many of the things they do. So you can either have effectively, if you take a left invariant Riemannian metric, which is what we will do, you have a camera-centric coordinate system based on the camera. If you take a right invariant Riemannian metric, you have an object-centric representation. So for example, and this becomes very important for lots of problems like grasping and robotics, right? So if you have a robotic arm that's supposed to manipulate itself, control, and then go grasp something and pick it up, you need to know how you are going to be able to reconcile the different representations. Like say you have a camera looking at it, there are notions of invariance that you need to worry about, okay? So I won't go into the details of why, this is a sketch of a proof for why there is no bi-invariant metric in SE3, but we will ignore that for now. There is another problem with the scale issue. If you remember, when we looked at the rotation case, we said that the intrinsic measure, the distance measure that I mentioned, I should have been more explicit about it. The intrinsic distance between R1 and R2, let's say given two rotations, is what did we do? We did a left invariant shift, and then we measured the distance between the identity matrix and, say, R1 inverse R2, right? That's nothing but that distance is nothing but the magnitude of the rotation angle that will take you from R1 to R2. In other words, the natural metric that is induced in 3D rotations has a nice physical meaning. It's actually the angle, the magnitude of the angle of rotation. So it's in radians, let's say, right? On the other hand, in translation, well, you can define translation in whatever units you want, right? You can have in millimeters to kilometers. It's arbitrary. You can pick the unit that you want to define. And I hope you can immediately see that there's a bit of a problem there, because you're now, in the case of Euclidean measurements, you're mixing things up. On the one hand, you have rotations, which have physical meaning defined in terms of actual angles that are again bounded by between 0 and 2 pi. Translation is firstly unbounded, but secondly, if you scale things incorrectly, you're going to get, the metric is not very informative. For example, imagine taking the average of these two elements, right, on the group. Let's say this is in meters, translation is in meters. And now if I were to do this, what do you think is going to happen? You're going to get a different answer, right? If I do this in centimeters, if I define t in centimeters, because the rotation is unit norm. So essentially all the elements of R are essentially between plus minus 1. Right? So their scale is fixed, whereas this scale is really arbitrary. So if you are not, so the problem with the Euclidean metric is that it does not have a good physical meaning, if you will, right? Because you're mixing up two completely different notions of rotations and translations into a single metric. So, the hack, if you will, is to just scale everything so that translation is of the order of 1. That kind of, that just, it's sort of arbitrary, but it makes sense in an empirical context. Okay, so having said that, this is just to sort of motivate the idea. We've already seen this, that you need to align things together. So imagine, many of you would be familiar with the ICP algorithm, which allows you to align individual pairs of scans, and so that's a pretty standard approach to doing it. And so now imagine you have an object on a turntable, and you're rotating the turntable and you're taking scans of it. And so what would you do? You would do individual alignment of scans using ICP, but eventually, when you come back, you're going to have a loop closure problem because the individual errors have accumulated, right? So for example, the very well-known Kinectfusion algorithm essentially just effectively does this very efficiently, of course, but it uses ICP and it builds an intermediate representation as it goes along. So if it makes an error anywhere in between, it cannot recover from it because it does not have a global view of the entire data set that you have. On the other hand, if you could wait till you acquire the entire data set, because Kinectfusion is doing it in real time, but if you could wait and collect all your data and then try and do a reconstruction in this case, then, well, you could notice that, well, the first one and the last one also have a relative motion relationship that I can define. And I can throw that into my set of constraints. So what you see in red here is the minimal spanning tree view graph that you would get if you were to just align the first with the second with the third scan, and so on and so forth. And here you could just simply add a single edge to complete the loop, right? And you could also add additional relationships that you may have. So that now your view graph is richer. And once you do that, you can actually now enforce the constraints that your solutions need to satisfy to be better. Because remember, if I were to just only use the red edges, then I'm going to start getting drift in my solution. And then this last camera is going to be very far from the first one. but that's going to be inconsistent from the relative motion that I estimate here. So what is that going to do? That is going to force my errors to be redistributed more uniformly. I mean, that's the whole key that motion averaging is actually leveraging, right? That if you take all the relationships simultaneously together, then you can actually enforce that they are as consistent as possible. So the errors get distributed more uniformly than if you were to just allow a causal kind of relationship, in which case you will have drift. So you can do various things with it. I'll just show you some. Yeah, so you can improve on solutions because now you have a batch view. You can essentially embed the motion averaging process into the ICP method, and you can get a multi-view ICP form. I'm happy to talk about it offline if people are interested. So you can, and then you can also do this robustly. For example, the problem of failure of reconstruction in the presence of outliers that I showed you earlier can be addressed. Here are some examples of reconstructions that you can have. This is a life-size statue of Mahatma Gandhi at his ashram in Western India in Ahmedabad. And this is our reconstruction with about 30 scans. Yeah, so you can actually do, and so so once you take a global view of the problem, you can actually stitch things together in a consistent fashion. In the beginning, when we were talking about motion groups, remember I'd mentioned two types of group actions. One was where the elements of the group act on each other and you get a third element of the group, and one was where the element of the group acts on, in this case, points in 3D space, and you get a transformed point. And in the case of Euclidean motion averaging, you can do both. So for example, this is what we have looked at till now, right? So you take relative motions and then you fit them. But you could also look at something like this. Look at what is this relationship saying. Imagine I have a point in a globe in my canonical coordinate system P0, and I apply a transformation MK. I get a representation in the new coordinate system PK, right? So now what I could do is I could just write it in this fashion, and what this is simply doing is taking all matching points, mapping them all into the same coordinate system, and then measuring differences in distance. Yeah? And once you do that, you can set up an optimization. It so turns out that, again, in the interest of time, I'm not going to go into all those different algorithms. It so turns out that way back in 96, 97, people were actually doing it without quite realizing that that's, posing it in this fashion. And there are some essential differences in the optimization that they do. There is some unpublished work where we can actually show that this can be very efficient. This can be very efficient and very accurate, and it can actually sort of solve the overall 3D alignment problem very, very well. Yeah, and it has some nice theoretical properties also. So you can do this for various kinds of problems. For example, if you have planar scenes in your data, then you can solve the rotation problem just simply using the normals for the fitted planes. They're going to be very accurate, and you can get pretty good reconstructions. I'm just going to take 2 minutes and then wind up. There is, like in the case of 3D rotations, there is also a relaxation form for SE3, where you ignore the geometric constraints of the problem, embed it in the extrinsic space, and then try and solve it. Yeah? So it more or less follows the ideas that I mentioned earlier. If you're interested, you can look at this paper in ECCV 2016, which sort of lays out all of these different relaxation ideas and how to solve this in the presence of outliers and so on and so forth. And here are some results that you can get. And the argument for their work is that it's much faster than many of the existing methods. Okay, so SE3 essentially, in conclusion, is also very useful. I mean, doing motion averaging on SE3 is also very useful, and you can actually gain a lot by looking at it in, instead of just doing it in an incremental fashion that like people do with Kinectfusion or other variants of it, you can, if you look at it in a batch form. There's also, I think, a strong similarity with problems in SLAM, except that in SLAM, the view graphs that you get are quite different in nature because you have very smooth motions and you have sort of temporal consistency of the data that you acquire. And so that's something that's actually of interest here. So, okay, so let me conclude. So this is a relatively new paradigm of doing, solving the camera motion estimation problem where you just sort of try and define a unified representation of camera-camera relationships. We also seen that the Lie group structure is very elegant and very powerful in the sense that we can actually use it very efficiently for our purposes, and we can also embed robustness into the algorithms to get not only efficient solutions but accurate ones. And it allows us to also, today we have a significant understanding of both the properties of intrinsic and extrinsic methods. So there still are obviously important questions that are open at this point, or at least are of interest at this point. So one is scaling, right? Everyone wants to solve even bigger and bigger problems. So scaling is still an issue. But we also need a deeper understanding of the global properties of intrinsic methods. Intrinsic methods have the elegance of the Lie group structure, but they're kind of hard to analyze. So most of the things that we can say are really local in nature, whereas many of those semi-definite relaxation kind of forms can give you something, in terms of the optimality of the relaxed problem, if you will, right? So there is more work, interesting work that can be done in terms of understanding the geometric properties of these representations, although I must say that they're somewhat hard. There's also maybe we could consider looking at more complex motion models than just rigid forms. It's not clear exactly the best way to do it. I personally also feel that now there's increasing convergence between, people did structure from motion for a long time in computer vision. Robotics guys did lots of SLAM things. And then you look at it and you realize inherently, it's more or less the same kind of problem at a certain level of abstraction, of course. So the question really is, how do these two things fit together, if you will? Yeah. So I'll stop here. These are my students who made some of the figures. I'll stop here. Thank you for your time, and I'm happy to take questions.